I think we're going to get started. Thank you for coming to our talk at the very end of today. My name is Jen, and this is Nima. Both of us have worked on Diego, both for quite some time, actually. And both of us have been involved in the Eirini project, so we thought it would be a cool experience to give this talk together as people that have experience with both Diego and Eirini. So what we're going to do today is first just go through a really quick overview of how CF works at a very high level scope, so you understand where the schedulers fit into the overall picture. We're going to talk about the history of workload schedulers in Cloud Foundry. Then we're going to go through the architecture of Eirini and Diego and compare those. And then we're going to walk through a couple scenarios to illustrate more concretely how the different schedulers are similar and where they differ. So this is the very quick CF architecture overview. On the left, we have this, let's say, app developer machine. And these are sort of the subsystems that you find in an essential Cloud Foundry distribution. So for example, when you run like a CF login from the command line, that's going to go and hit UAA, which is responsible for authentication and authorization via the Go router to resolve where the UAA lives. The next thing a developer might do is do a CF push. That's going to go talk to the cloud controller. The cloud controller is sort of the front end for interacting with the Cloud Foundry system. It's the API that gets hit when you're using the CLI or any other tool that's interacting with Cloud Foundry. The cloud controller in this case is going to stage your application. It's going to take your app bits and then combine it with a droplet, and it needs a container to do all of that work. Combine your app bits with a build pack to create a droplet, and that piece of work gets sent over to the workload scheduler in a staging task. The result of this is what we call a droplet, and that gets stored off in a blob store. The next thing that the cloud controller is going to do is start your app. This creates some long-running processes that the workload scheduler maintains and keeps healthy. In this case, we're going to assume that there are 3 instances of your app, and the workload scheduler is keeping those healthy and active. The workload scheduler then also registers these app instances with the Go router, so the Go router knows where it can find instances of your running app, so that when the developer or an end user tries to curl your app, the Go router knows exactly where to direct the request to. At the same time, any output that's going to standard out or standard error is being directed to the logator subsystem. And it's collecting all the logs from all of your app instances. And then as a dev, you can run CF logs and get all the logs from all the instances of your app. So this is really high level picture, and we've intentionally called this thing the workload scheduler without naming it Diego or Eirini, because we're going to get into more details about how those actually work very soon. So quick history of schedulers in Cloud Foundry. In the beginning, we had a component called the DEAs, or the Droplet Execution Agents. These were tightly coupled to the cloud controller. It was really tough to add new features, really brittle, and there wasn't a really strong line between the cloud controller and the component responsible for running your staging tasks and your app workloads. So in 2015, around that time, we migrated to Diego, which introduced a very strong line between the cloud controller and the component responsible for running your apps and running your tasks. It allowed us to develop a lot of new features and add those to the system. This was written in Go. The DEAs were written in Ruby. So this was called Diego because it's DEAs written in Go. And now we're like in the exploration phase of Eirini. This is the idea that, well, since we have this like strong boundary now between the workload scheduler and the cloud controller, why don't we just put Kubernetes there instead? And to reuse Kubernetes for our app workloads and our staging tasks. Now I'm going to hand it off to Nima to talk about the details of the schedulers.
All right, thank you very much. A quick disclaimer that we're going to show a lot of diagrams in this presentation. So if you get confused, feel free to interrupt me and tell me to just slow down or, review things. But this is the high level for Diego. You see the components that are highlighted. On the left, we have the auctioneer, the BBS, and the database. Then we have the cells that are essentially the VMs with the rep and the executor as the processes, Garden as the container runtime, and then blob store, log aggregator, and GoRouter Cloud Foundry components, right? We're going to come back to these. But then the Eirini architecture, basically with Kubernetes as the scheduler. You see on the left, we have Eirini and the Kubernetes API server and the scheduler. In the middle, we have worker nodes, which again are the VMs. On the VMs, we've got the kubelet, the kubeproxy, and also the container runtime. And we also have the log aggregator and GoRouter as the Cloud Foundry components. So let's put them side by side and do a comparison of the two schedulers. So first of all, the APIs. As I mentioned, for Diego, we have auctioneer, BBS, and the BBS database. And BBS essentially is the API for the container scheduler and for the runtime of Cloud Foundry. For Eirini, we have, of course, the Eirini component, which serves similar to BBS as the entry point to the scheduler. Then we have the API server and the Kube scheduler that are responsible for actually scheduling the running of application instances. And we have etcd as the database store. So the source of truth between Eirini and Diego are the databases, and the BBS database and the etcd in Kubernetes. Stark and Wayne has a very nice article comparing the source of truth between Kubernetes and Cloud Foundry that if you're interested, you can also read. The next phase of it is the scheduler, right? So the scheduler in Diego is auctioneer. And auctioneer is a component that looks at the cells or the VMs, measures whether they have enough resources in terms of memory, disk, and also CPU resources. And then takes the request for the instances and based on the available resources and some other constraints, decide on where each application instance needs to go. This, on the Eirini side, is handled by the Kubernetes scheduler, right? So the Kubernetes scheduler does a very similar task of understanding what is the resources available on the node and how the application instances are going to be distributed. We have workers, which are the VMs that actually run the application instances. Workers, in the case of Diego, are managed by a process called the rep, which collects all the information from resource usage from each of these virtual machines, forwards them to the auctioneer for the auctioneer to make decisions about placements. And then later on, when those requests come in, contacts the runtime and tells the runtime to run the application instances. And for the case of Eirini, this is done by kubelet. Basically the same set of actions, collecting resource information, letting the scheduler know about the available resources, and then the scheduler taking care of placing instances. Then we have the container runtime in both architectures, right? For Kubernetes, the container runtime is actually pluggable. You can have containerd, you can have Docker daemon, you can have Rocket, you can have Creo. But for Cloud Foundry, it's Garden. And Garden is basically an API to run C, which is in charge of running application instances. And it's not as pluggable, as flexible the way it is with Kubernetes. So for routing, with Diego, we have the route emitter, which basically receives information about the IP address of each container and the port for the application, forwards that information to the GoRouter, and makes the application instance routable. For Kubernetes, this is done through kubeproxy, which has some understanding of the IP address of the node. And also when a pod starts up and running, it collects the container port and then rewrites some of the IP table rules on the node so that it actually makes that information for routing of an application instance available. That information that gets relayed to Eirini, which then contacts the GoRouter and rewrites the GoRouter information in order to make the application instance available. All right, so let's have a deeper look at the scheduler, right? From a Kubernetes manual, the scheduler in Kubernetes does two things. It does filtering and it does scoring. So by filtering, it basically selects the set of nodes or the VMs that can run an application, and then it runs a scoring algorithm in order to decide, okay, which one out of all the ones that are capable of running an application instance can in fact run that application instance, right? And the node with the higher score basically picks up the instance and runs it. Let's look at the source code. So you see for filtering, there is like a part for filter zone, which actually does the filtering of nodes. And for scoring, there's a part that actually goes through all the VMs and essentially says, hey, pick this particular VM, which has a higher score, right? Pretty clear. So the left, we have the Kubernetes scheduler. The part that I didn't mention is that the code that I showed you is in fact Diego's auctioneer, right? So what makes it clear is that, in terms of design, they're very similar in what they do, in filtering and in calculating the score. But the Kubernetes scheduler basically does the filtering and the scoring based on two sets of criteria. Predicates, which are the hard constraints. So if a node doesn't fit a predicate, it's actually out of equation. It's not going to be considered for scheduling. But priorities are softer constraints, where, like a node that fails a priority still has a chance in basically having a placement of an application instance. On the Diego side, we have the scores again, which are calculated based on the available resources for a given VM in terms of the available memory, the available CPU. And obviously, like the algorithm works in such a way that if you have a VM that is already serving less load, it has a higher score to actually host new application instances. And then Diego also has some constraints. For example, the root file system constraint, which is like in a Diego world, in a Kubernetes world, is a hard constraint. Essentially, if your application needs a particular file system requirements, and then the scheduler makes sure that your application actually ends up on that particular node. But the one thing that is interesting is that if you look at the set of predicates and priorities for Kubernetes, there's a lot of things that you can configure for this scheduler. For Diego, on the other hand, scores and constraints or predicates and priorities are a lot simpler. Scoring is only for CPU, memory, and disk, and constraints are like a handful of options that you can configure. So in that sense, the Kubernetes scheduler is a lot more flexible, and you can do a lot of different considerations in order to decide how to do scheduling. One thing that's very interesting with the Kubernetes scheduler is that it implements a pull-based model. When a pod is required to be scheduled, what happens is that it's placed in a queue, and then the scheduler looks at that queue and says, hey, there's a pod that requires a node. So I'm going to take it, do my scoring and calculations, and then decide where to place it, right? So this is good in the sense that it's easily decoupled, in the sense that I can bring a different scheduler, look at the same queue, look at the pods that are not scheduled, and decide about how to place them, right? Where it's difficult is that it's hard to scale. So if you want a scheduler, you bring it to the Kubernetes world, and then all of a sudden your queue starts growing long. There is not really an easy way for you to load balance your scheduler so that you have multiple instances working on that queue. But in terms of decoupling, as you know, writing custom Kubernetes schedulers is a very common thing that a lot of people do. On the Diego side, the scheduling is more on demand in the sense that BBS, which is the API server, goes to the scheduler and says, hey, I've got these requests for these number of applications. Please go ahead and find nodes for me. The good side of it is obviously that you can easily load balance it or basically scale it by putting the scheduler behind the load balancer. As the BBS starts hitting the auctioneer more and more instances of auctioneer can potentially operate on the requests that come in. This is not the case with auctioneer, really, because auctioneer is only a single instance application. So redundancy is mostly in the form of a master-slave kind of model. But essentially, if auctioneer wants to scale, it can. But the problem is that because there's a tight coupling between the BBS API and the auctioneer endpoints, it's not really easy to write custom schedulers. So the notion of custom schedulers in case of Cloud Foundry is not very common. One of the interesting reads that you can have in the same domain is like to message bus or not. In case of distributed systems, it's a nice blog post that Netlify has written. Okay, so the major takeaway of all the conversation that we had here is that the schedulers between Eirini and Diego are in fact very similar, right? So this is not surprising, and this shows why Cloud Foundry has been super successful in terms of having a scheduler and not needing Kubernetes for the most part, right? Okay, so with that, I'm going to very quickly go over what happens when you push an application for the case of Diego, and then compare it with Eirini. I'm going to keep it at a very high level, but if you want further detail, I think we can have that conversation after the talk. All right, so in case of Diego, when a request to schedule an application comes in, obviously the first component that it hits is the BBS, which is the API for the scheduler. The BBS then takes that information for the application, which consists of how much resources the application requires and what are the hard constraints for placement of this application, and takes that information to the auctioneer and asks the auctioneer to go ahead and schedule the application. Auctioneer then looks at all the information that reps have provided in terms of available resources for the nodes, take everything into consideration, does its scoring, does its filtering, etc., and eventually finds the particular node that is the candidate for deploying the application instance. Contacts that particular rep on that node and says, hey, okay, you've been chosen to do the deployment, go ahead and deploy an application instance. The rep then contacts the blob store and downloads the application artifacts. These application artifacts are the droplet for the application and potentially the build pack that the application requires to run. And once that information is fetched, it updates the BBS and says, hey, I've received successfully all the artifacts and I can try to run the application instance. At that point, it contacts the runtime, which is Garden, and says, hey, this is the code for the application. Create a container, mount all these application artifacts into the container, and run it. So Garden goes ahead and does it. And if it's successful, then it starts reporting information back on the execution of the application instance and pushes the logs out to the log aggregator, contacts the route emitter, telling the route emitter about the IP of the application instance and the port. And then the route emitter goes ahead and contacts the Go router in order to update the Go router so that the application is routable, right? Now let's look at Eirini. With Eirini, what happens is that the request from Cloud Controller this time goes to Eirini, which basically serves as the API for the system. Eirini then contacts the API server for Kubernetes and says, hey, I've got this request to run this application instance, create a pod for me. And so what API server does is that it records that information in the etcd database, and then puts the request for the pod in a queue that the scheduler actually monitors. So the scheduler notices that, oh, there's a pod that needs a node to be placed on, and then it goes, contacts all the kubelets on all the nodes, collects all the node information, and then does its filtering and scoring calculations, and then chooses the node that is responsible for running the application. And tags the pod with the node that is responsible for actually running the application. The kubelet on the node then watches the number of pods that are required to run on that given node. And as it notices that there is a pod assigned to it, it goes and picks the pod and it starts looking at things that it needs to do in order to get that pod up and running. That involves contacting the container runtime and telling the container runtime to create a container, and then mounting the application information into that container. And from that point on, it's very similar to what Garden does. It starts contacting the registry for pulling the application artifacts, which in the case of Kubernetes is the image for the application, downloads the image, and then starts that image on the node. And once that happens, it starts pushing the logs out to the log aggregator, and then the kube proxy, which is the other process on the Kubernetes node, rewrites the IP table for the node to make that application instance accessible, and provides that information back to Eirini in the form of labels. And Eirini uses that information to contact the route emitter and tell the route emitter about the application instance, which then sends that information to the Go router and makes that instance available. So with that, you get an instance up and running on Eirini. And then Jen is going to talk about another case of how this is done between Diego and Eirini for RootFS updates.
So one of the important things that Cloud Foundry can do is to make it very easy to update the RootFS that your app is running on top of. So this is the OS image that your app is using. By default, in CF deployment, we use CF Linux FS3, which is based on Ubuntu. And we're going to walk through now here how this flow works when you have a new version of this RootFS in both the Diego and the Eirini worlds. So we're going to start with Diego. Diego is built to run really well on Bosch. So we're also going to assume that there is a Bosch involved here. In this case, we have 3 Diego cells. Each Diego cell has a version of the RootFS. And then when Garden starts up a container, it also includes the RootFS that cell knows about. So we're going to start by assuming that the Bosch director has been informed that there is a new version of the CF Linux FS3 release. The Bosch director is then going to go contact one of the cells and say, okay, I need to restart the rep job in order to update the CF Linux FS3 code that's on that cell. As part of that, it needs to drain the rep. This is a special script that the Bosch director runs on the Diego cell. The rep interprets this by saying, okay, I'm draining. In my language, that means I'm evacuating. So now it's in this special kind of mode. It's not going to schedule any new work on this cell in this evacuating mode. The rep is also going to inform BBS that all these app instances need to be placed somewhere else, because we don't want to have any downtime when we're doing this kind of an upgrade. The auctioneer then contacts the other cells and asks, hey, can you take on this work? The cells, in this case, say, yep, we can take these app instances. And then these other reps start up some extra containers representing the work that's now being moved off of cell number 1. And the route emitter is informed that we now need to have the Go router know about these locations of these app instances. And similarly, we need to deregister the routes that are pointing to the evacuating cell. After all of this, the rep can then tell Bosch, yep, I'm done draining. You can go ahead and restart all the jobs on this VM. That's safe to do. So now we've restarted our CF Linux FS3 job. We've restarted the rep. We have no workloads running on this machine anymore, and we're in a totally clean state. Then Bosch will go ahead and do the same thing to all the other cells, and that's how all of our cells are going to get an updated RootFS. So let's look at Eirini. It's quite a different flow in Eirini. There is no knowledge. So in Diego, the idea of a RootFS is baked into the cell itself. In Kubernetes, each individual image that is running an app workload contains the RootFS. This gets bundled by the registry in this case. So when you are starting up a pod for an app workload, the container runtime reaches out to the registry. The registry grabs a droplet for your app and then sticks the RootFS onto that image as the RootFS layer. So the very first thing that's going to happen in this flow, so here what you see, this 8.6D, that is a particular version of a RootFS in this case. This is EiriniFS, which is a repackaging of CF Linux FS3. So the first thing that's going to happen is we need to update that image on the registry. This means that any new pods that are going to get created are going to now have the correct new version of the RootFS. However, we still have all these existing app pods, and they need to get updated too. So Eirini is then going to update the stateful set that represents all of these app pods and controls all of these app pods. It's going to update a label on that stateful set. By updating this label, and this label, the value of the label corresponds to the version of the RootFS, by updating that label, it's going to cause Kubernetes to say, oh, these app pods are out of date. I need to go restart all of them. And when we restart them, that means the container runtime is going to have to reach out to the registry again and get the new version of the container image. So then we're going to go through all of the app pods one by one and update all of these pods. So in summary, like Nima said, there are lots of similarities across the two platforms. There are just like slight differences in how certain things get accomplished, but by and large, they're solving very similar problems, and they're sometimes doing it in very similar ways. In general, Kubernetes is a lot more pluggable. You can choose what container runtime you want. You can modify the scheduler if you want. You have a lot more control. Whereas Diego is a lot more of a configuration that we know works really well together. You can't go in and add your own container runtime, but we guarantee the Garden works really, really well for Cloud Foundry. With Kubernetes, you have more of a declarative configuration. And when things go wrong, if you're using Kubernetes and you're already familiar with the kubectl command line tool or other Kubernetes tools, you can use that for troubleshooting and debugging. With Diego, you're probably going to be using like Bosch skills for troubleshooting when things go wrong. But by and large, there are way more similarities than differences in the two, which is why it was pretty natural for us to move to replace Diego with Kubernetes. And with that, are there any questions?
What kind of registry are you using for Eirini? Can you speak a little bit about that?
Sure. Right now, we're using the bit service, actually. We're using the bit service because the bit service, for those who are not aware, is sort of a project meant to pull a lot of the blob store operation stuff out of the cloud controller into a separate component. So if you're using the bit service, then that component already knows about droplets and stuff. So what the Eirini team has done is repurpose the bit service, saying, well, since this thing already knows about droplets and knows where they live, we can also just put on a registry on that, and then we have access to the droplets and we can kind of sit in between. And as long as we have an Eirini FS, like a RootFS, we can easily just like shim that in whenever a request comes for an image.
Add to that. So essentially, the Docker image that is used for application instances in Eirini has two layers in it. The base layer is the Eirini FS layer, which is like a pretty big tar file that I think it's probably 900 megabytes or something. But that serves as the base layer, which can have, you know, the CF Linux FS3, for example, in it, right? And then there is the other layer on top of it that gets created on the fly when you actually build an application instance. And the way it's done is that when Cloud Foundry runs the build pack operations on a given application source code and creates the tar file for the droplet, then it modifies the Docker manifest for the image by adding an extra layer on top of the Eirini FS layer, referencing the newly created droplet as the additional layer on top. And then creates that as, so what bit service does is that bit service actually provides this shim on top of that combination of tar files and makes it available to the container runtime in Kubernetes in the form of one image. So when the container runtime contacts it, it downloads the entire thing, all the different layers, and then can run it. Yeah.
Just as a follow-up, just a quick follow-up question. I think Bit Service announced that it's only in maintenance mode for Eirini. So will you be switching over to a new kind of registry?
I think the plan is to switch to a default registry, right? Or essentially allow the users to bring in their own registries. I think with Kubernetes relying on, you know, just standard registries, there is not really that much need for, you know, a standalone registry that is managed by Cloud Foundry. But instead, what can be done is that you actually create an image and then push that image that you create to a standard registry and then use that instead.
I think that also relies on a new kind of a replacement workflow for staging compared to how we do staging right now. I think there's discussions going on about using some of the KPAC stuff, I believe. But that's kind of more future looking. I'm not sure exactly where that's going to go.
There used to be a mention of work around scalability into Eirini, which was not yet matching Diego. Can you tell us more about issues encountered and current status?
Sure. So the major scalability tests that were done with Diego were 1,000 nodes, 250,000 application instances, which was, I think, still to date, probably one of the biggest scalability tests ever done. What we've done with Eirini is slightly different. I think the biggest scale that we've reached with Eirini is probably like 30 nodes or 40 nodes with 2,500 application instances. So almost like 10 times smaller than the scalability test that we did for Diego. And there are a number of bottlenecks. One of the bottlenecks is with the staging itself. We noticed that, with the staging, for example, the amount of time that it takes when the number of instances that you want to create in parallel, as the number of instances increase, the amount of time that it takes for those images to be created actually grows relatively exponentially, bit services being one of the bottlenecks, right? So there are a number of bottlenecks that the team has identified. Another thing that is a problem is with upgrades and rollout of the new instances of the application. I think Eirini still has a little bit of problem, doing like live rollouts. So there are a few cases where, and Eirini heavily relies on SCF, at least the way it stands. And there are some complications in terms of scaling the SCF components too, which slows down the overall performance of Eirini. So altogether, I think the containerized model is probably going to have to be modified to a good extent for Eirini to be more scalable. That's, I think, the way we see it.
I think we're at time now. So if you have more questions, either find us, or there are also some Eirini team members in the back that you can ask. Thank you all for coming.
Thank you.